everyone. My name is Haewon, and I'm really excited to talk about our work on fairness without imputation, a decision tree approach for fair prediction with missing values. And this is joint work with Haewon and Flavia Kalman at Harvard. Before I begin, I just want to give a brief introduction of myself. I did a PhD at Carnegie University. And during my PhD, I worked on a topic that is a little bit different from what I'm going to talk about today, which is reliability in machine metrics. So in my PhD, I thought about large-scale computing systems where we have thousands of compute nodes. And when we have thousands of compute nodes, there could be machine unreliabilities, such as some nodes might fail in the middle of computation, and some nodes might not respond as fast as other nodes. And I thought about how to apply ideas from information theory to deal with these machine unreliabilities in large-scale computing. And then I did my postdoc at Harvard. And here I switched the direction a little bit, and I thought about reliability in human metrics because machine learning algorithms these days, even if it's really reliable in machine metrics, such as accuracy or computation time, if people cannot trust the algorithm, because it doesn't have the quality like fairness or accountability, and people don't want to rely on those machine learning algorithms. So especially, I was looking into fairness issues in machine learning algorithms applied to education. So this work will be the work I did during my postdoc at Harvard. And currently, my postdoc contract at Harvard ended on May 31st, so I'm officially jobless. I have no income and no medical coverage, but I feel very happy right now so far. And in September this year, I'll be joining UC Santa Barbara's ECU department. So if you have any tips about how to spend this little period of joblessness, or if you have any advice for a starting faculty, I would love to talk to you during coffee breaks or during the conference. Okay, now let's talk about missing values. So missing values are really common in real-world data sets. And it is even harder to find a data set that doesn't contain any missing values. To give you some examples, in survey data, people sometimes don't want to answer some questions because they don't feel comfortable answering those questions. And in electronic health records, not everyone takes the same set of medical tests, so some of the entries will remain empty. And in police report data, when police officers are filling in police reports, they don't fill in all of the details, so some entries will remain missing. And one important observation I made while I was working with education data is that the data missing patterns depend on sensitive group attributes such as race or gender. And this is an example of missing statistics from an education data set called High School Longitudinal Study data set, and I'm showing missing rates of white Asian students and Black, Hispanic, and Native American students. And these are 3 example variables in the data set. So the data set contains student survey variables and parent survey variables. And you can see that in all of these variables, the missing rate is higher, consistently higher in Black, Hispanic, and Native American students. And some variables, they have really significant difference. So if you look at this third variable on secondary caregivers, highest education, the missing rate difference between white Asian students and Black, Hispanic, and Native American students is 15%. And we train machine learning models that make critical decisions on people that have high stake consequences, such that we can make education-related decisions such as school admissions or grade assignments, or make medical decisions or bail decisions on data sets that contain missing values and that have disparate missing patterns across groups. So a critical question is, can we train a fair model when there exists disparate missing patterns across groups? The first question that might arise is then how do we quantify fairness? And in this work, we focus on a class of metrics called group fairness metrics because we look at differences between groups such as female and male or white and Black. I think this crowd might be more familiar with this concept, but I just go over this really quickly. So we define S as a sensitive group attribute. And for simplicity, we are going to assume that S is binary. So S equals 0 is minority, and S equals 1 is majority. And we also assume that we are doing binary prediction, and we denote this prediction as white hat. And the basic underlying idea of group fairness matrix is that the performance of a machine learning model should not depend on these sensitive group attributes such as race or gender. So depending on how we define the performance of a machine learning model, there are different group fairness metrics. For instance, statistical parity look at positive rates, which is the ratio of people getting the positive prediction. So statistical parity metric focuses on equalizing the number of positive predictions in two groups, S equals 0 and S equals 1. And another example is equalized opportunity. It wants to equalize false negative rates. So it wants to equalize the number of people getting false negative predictions in group 0 and group 1. And accuracy parity is similar, but it focuses on equalizing accuracy between the two groups. And in the ideal world, we want these group-wise differences in this matrix to be 0, but that's not always possible. So we think of a model that has small differences in this matrix as a more fair model. And in the current fair machine learning literature, a large body of existing works focus on reducing these group-wise differences as much as possible when we train a machine learning model. But the problem is when they develop and evaluate these new fair machine learning algorithms, they use clean and curated input data that don't contain any missing values. However, in real-world data sets, they are usually not as clean, and they often contain missing values. And these missing data are processed in the stage before we train the model. So if we just focus on reducing the bias when we are training the model, what about the fairness issues that could arise in the data pre-processing stage? So now let's look at what exactly we do in the data pre-processing stage to deal with missing values. So we often perform the process called data imputation, where we fill in missing values with a new value using such as mean imputation or median imputation or k-nearest neighbor imputation. You can also decide to drop the rows that have missing values, but that approach is usually performed worse than data imputation. So this problem of how to deal with missing values in a fair way has not gained a lot of attention from the literature, and we only found 2 existing works in this direction. The first work is Fernando et al., and they did an empirical study on how different imputation techniques impact the group fairness metrics in the final prediction. And Wang and Singh proposed a re-weighing approach that assigns lower weights to data points that have a lot of missing values to achieve fairness. And our work poses a more fundamental question, which is it sufficient to do data imputation first and apply a fair learning algorithm on the imputed data? In other words, if we consider all of the steps that come before model training as a black box and simply apply a fair learning algorithm afterwards, is that sufficient to guarantee fairness when data sets have missing values? To answer this question, we have 2 main contributions. First, we analyzed the risk of this disjoint process of imputation and training theoretically, and we proved 3 different theorems, and each theorem shows different risks of disjoint imputation and training. So the first theorem shows that the performance of imputation itself can be biased, and the second theorem shows the risk of mismatched imputation methods between training and testing time. In the last theorem, we showed some fundamental results that there is no universally fair imputation method for different downstream learning tasks. And inspired by this theoretical analysis, we proposed a new algorithm called fair-MIP-forest that integrates data imputation and learning into a single algorithm. And then we did some numerical analysis that this fair-MIP-forest approach outperforms doing imputation and learning separate, fair learning separate. So let me go into more details. And I don't know how much time I have. 6 minutes. Okay. So maybe I zoom through a lot of details. So this is more details about theorem 1, but maybe I skip through this, but I'll be there at the poster session tomorrow if you're more curious. And maybe I talk a little bit about theorem 2. So when data scientists release a trained model, they might use some imputation method when they were training a model, but they might not disclose the imputation method when they're releasing the model. So when we are using the model we got from some entity, then we have to choose our own imputation method that might not exactly match what was used during the training time. And that could aggravate the existing bias. So this is the testing time performance gap between group 0 and group 1. And this is the training time performance gap between group 0 and group 1. And because of the distribution shift from the training time and testing time caused by mismatched imputation methods, it shows that even if the data scientists who trained the model could guarantee some fairness metrics, they might not exactly guarantee fairness during the testing time. And the last theorem, which shows the universal impossibility result. And I'm not gonna go into more details, but let me just try to give you the takeaway message. So what this theorem says is, if we have 2 different model classes we use in the downstream task, there is no universally fair imputation method that could guarantee fairness and accuracy in all of these different downstream tasks. Okay, so now I want to talk a little bit about our fair-MIP-forest algorithm. So this is a decision tree-based algorithm. And we are using decision trees because they enable us to avoid imputation altogether. So we can do that by using the idea called missing in attributes. So instead of doing the imputation to fill in the missing values, we can just leave missing values as they are. And then we just, when we are splitting at each branch, we just decide whether to send the missing values to the left or to the right. So it's like using data missingness as an attribute. Okay, so we can deal with missing values in the decision trees. Now all we have to do is incorporating fairness constraints when we are training a decision tree. And for that, we are going to use mixed integer program formulation of decision tree training. So usually the most common way of training a decision tree is optimizing some metric at each branch locally. But instead of doing that, we are formulating a decision tree training as a global optimization that have explicit loss function. So it has a lot of notations, but you don't have to worry about any of them. And I just want to give some important points. So we have explicit loss function. So this is, the first one is the user loss function that could be error. And now we have a fairness regularizer. And using this fairness regularizer, we can incorporate statistical parity or equalizer odds or accuracy parity, which are fairness metrics I mentioned earlier. And then splitting at each node can now be formulated as binary variables. So this is integer variables, and the threshold will be continuous variables. So this whole thing is mixed integer program. And because this is integer program, it has high computational complexity. But what we observe is that even though we don't find the optimum of each tree, if we have an ensemble of many trees that are trained for, say, 1 minute, then we have really, really good results. So this is a forest algorithm. Now I want to show some numerical results of their MIP forest algorithm. So what we want to do is we want to compare the performance of their MIP forest algorithm with using imputation, doing imputation, and applying fair learning on top of the imputed data. And then we use 3 different data sets: Compass, adult, and high school longitudinal study data set. And we benchmark 3 fair learning algorithms: disparate mistreatment, reduction subapproach, and equalized odds post-processing. And we also use 2 different imputation methods: mean imputation and k-nearest neighbor imputation. So this is the result on Compass and HSLS data set. And the y-axis is accuracy, and the x-axis is fairness, which is group difference in false negative rates. So here we are looking at equalized odds, equalized opportunity metric. And the higher curve means better because with the same amount of group difference, it means that we are achieving higher accuracy. And the circle ones are using mean imputation, and the square ones are using k-n imputation. And these overall, sapphire, and hearts are different fair learning methods. And we can see that in both Compass and HSLS data sets, the curve of their MIP forest sit above all the other methods, so we outperform performing imputation and fair learning algorithm separately. So as I mentioned earlier, this problem of how to deal with missing values in a fair way has not gained a lot of attention from the research community. So I believe there are so many more open problems we can tackle in the future. So first one is we're proposing an approach that doesn't require any imputation, but I think it would be really interesting to think about how to design fair imputation methods. And some other directions are, we looked at using decision trees and how you do fair imputation or fair processing of missing values with decision trees. But can we think of ways to incorporate these ideas into different machine learning models such as neural networks? And in missing values, dealing with missing values actually has really huge huge literature that have long history. And people usually perform multiple imputation. So instead of imputing one value, they impute multiple values. So how to make these multiple imputation methods more fair could be another interesting direction. And we can also think about other fairness metrics beyond the group fairness metrics I use, such as individual fairness or preference-based fairness or rationality. So that's the end of my talk. Thank you for listening.